robotics. And I know everybody's very interested to hear where we are on AI and when we'll get real-time information on what the composition of the stream is. Eric.
Good morning, everybody. Thank you for being here. Thank you for having us here. This is great. So how do you get invited to talk at a conference? You make a 5-line title with buzzwords in it, and then you get invited. So joke aside, I think we're going to talk about important things. This quote there, we are the robotic toolbox to the recycling industry. I use it, but actually it's not from me, it's from David sitting over there. So, but I use it since I'm the boss, I can do whatever I want. So there's a saying that was said a long time ago by this English philosopher that knowledge is power. Sir Francis Bacon. I used this slide in a show in UK, and I thought it would be great. Like everybody would go like, "Yeah, this is great," but nobody knew who he was. So, but anyway, the quote is valuable to us. I think that's what we're talking about here. Shortly about us, we're in the business to bring robotic picking. So we like to get the conversation around effective picking. We'll talk more about that, about how robots bring efficiency and value into the recycling industry. So that's what we do every day. We're out of Canada, so the funny accent is out of Montreal. There's 25 of us completely passionate about developing technologies that are going to bring real difference to this industry. Old people, young people, just people having fun and making great products. We're out there to resolve large issues. Everybody's motivated. We have several partners. We consider our clients partners. We like to have a relationship that is really close to them, because in the end, the robots are kind of a part of the family. It's a working tool there that is being installed and it can evolve. Fanuc is the robot company that we use. It's out of Japan. It's the most sophisticated robotic company with the biggest service network worldwide, and it's the toughest robot. That's a very important part of what we do. And we have financiers, we have clients, we have people that just are with us, supporting us, and we're glad to have them, and we're all in this together to try to do cool things with technologies. So why are we talking about technology? So the first thing we need to do is we need to see what's going on the belt. Oh, there's a laser. So here, typical camera. So there's a color camera that is looking at the material going by. We use 3D laser profiler. It's important to have 3D for analytics, for robot safety. We need to know what height we're going to pick. If we ram into material all day, the robots are going to break, the grippers are going to break, and we're not going to do anything good in the end. Hyperspectral, that's why we're here to talk about it. I think the segue was excellent. We edged our bet that we're going to make a more expensive machine that is going to deliver more value, because we put that sensor in from the get-go in all our products. We need to see the chemistry of what's going on, and I'll show why AI has several limitations to what it can do. So having that extra signal. So for those of you who are familiar with NIR, hyperspectral, well, we call it hyperspectral because it's sort of a NIR will look at certain wavelength and will identify plastic based on reflection of light. We look at a wider band of wavelength in the cameras we use. Gripper AI, I'll talk to that a lot. That's also part of the equation. If you're sorting, you need to pick. And if you need to pick, you need to grip properly. If you're not gripping, you're not doing anything. You can do all that fancy AI stuff. So what we call gripper AI is the intelligence of actually going and capturing products on the belt. And regular AI, what's most of us in the industry are doing is identifying an object, putting a little square around it, and that's what we do. But gripper AI, we'll talk more about that. sorry, there's some, I don't know, slide formatting issues, but doesn't matter. There's a significant issue in packaging changing all the time. So these packaging, well, this one is the worst we've seen. Every other month, this guy is changing his plastic for his lid. So how do you figure this out? There's no way. You can tell me whatever you want about AI, it's not doable. I can't myself can know. Actually, I have to flip it and use my glasses to see the little logo, figure out what's going on this. So if you can have the greatest AI in the world, these two lids are not going to be sorted with AI, only if we have really a hyperspectral that we can see. Same with these containers. They're flipping back and forth all the time. It's really hard to keep up. Your AI needs to be retrained all the time. It's limiting. And what about these crushed white, dirty white plastics? You tell me this is going to be sorted at 99% with only AI? We don't believe it. We know it's very difficult. So having that extra signal, for example, that lid, it's black and white. So now we know what's going on the belt, and we go for it for real. So reading the chemistry of the product is really important. Not having it, you can have the fastest robot in the world, you're going to bind together PP and HDP, so for whatever that's worth, that's still mixed plastic. So what does hyperspectral brings? Well, quality of sorting. We know about the history of sorting before we're shipping it out, and quality was so-so, but now we want to keep it domestic. We want to bring it as much of a quality as possible, so obviously quality means higher bale value, higher recovery. So higher recovery also, being able to see what's going on the belt, figuring out what you're going after, it's very important, obviously resulting in landfill diversion and more money, more recovery, more money in your pocket. So we talked about hyperspectral, that's great. So what is this? What is robotic sorting? And you have 4 functions in robotic sorting. So you need an eye, you need a brain, you need an arm, and you need a hand. So you're missing one of these 4, good luck, you're not going to sort anything. So having grippers is really important. So what is gripper AI? Is like, I'm sorry, I'm going to use some accessories here. So you're trying to go for this thing here, this cup. With a gripper, if I'm going for it like this, there's a potential interference with this bottle because this bottle is higher, and if I'm coming full tilt, the robot doesn't see. So everybody understand? We have a scanner in front. We get these data, we try to figure out what's going on the belt, and then we dispatch order to these blind robots. These robots are completely blind. They don't know what they're doing. They're going full tilt. They're just gonna go for it. So if I'm coming for this piece there, and there's another interference, what we call, so this sort of intelligence of calculating interference, pick strategies. So how do I pick this? Do I pick it on a long side, on a short side? Is there interference there? Pick dispatch. I have several robots, one vision system. Do I pick this one before this one? I should pick this one first, remove the interference so the second robot can pick the down one there. Very, very important. So that AI is a huge barrier to entry to most of people using only suction cup right now, because the suction cup is the center of mass tool. You go for it, you hope for the best, and it's working great. But when you start to do more convoluted sorting, you need that sort of intelligence built into, and destacking, the ability actually to destack because the stuff is overlapping on one or the other. So, and having grippers that can do this, that can take a cinder block and flip it. You don't do that with, we cannot do that with just suction systems. So the ability to actually maximize the performance, picking it on the right side, do it properly, having gripping strength, having the ability to move large objects. CND, it works. We don't use that in CND. We use it only in, we use that in CND, not in other. Now, I want to bring the conversation to something else, like what we call effective pick. Because there's been a lot of talk about robots out there and what we can do and how many moves we can do and all that jazz. But actually, we have something we call the robot validator, and I like saying that because it sounds like robot terminator. So what do? We put a scanner there, and we scan for a while, and now we see your stream. We see it all. So we can tag it. So tagging is, most of us out there can do this. It's now getting democratized. But now what do we want to do? So this is an example of a guy that has an aluminum stream after an eddy current. He's got contaminants in there, and he wants to get stuff removed to bring the quality of his aluminum up by picking stuff. And we established with the client that HDPE was probably one of the heavy fraction in that stream who should be first. So in order of priority, if we don't have time to do it all, let's do HDPE first, PET containers, PET bottle fiber, and so on. So the client said, if I'm going to remove things, I'm going to remove them in that order. Now, what do we do? So we have collected real data from real stream, and then we have identified all these boxes, and then we throw this at our simulator. We have a simulator that will simulate real robots, like this robot there. It will do exactly the same thing in the simulator as in real life, so we simulate it all. And what we figured, and then we run it for here, we run it, oops, sorry, back here. All right. So we collected 13 hours of material, like a full day. And this robot usually does, if we do the, we know can do 32 picks per minute. That's an M10 from Fanuc. You can go and buy it. Anybody can do that. But now, after we run all these, so we send picks. We send the first pick and it goes drop it in bin one. We send the second pick and we simulate this all. This robot is, by design, 32 picks per minute. But the way the stream is showing and how actually the robot's busy doing other things, actually this robot will actually do 23 picks in average per minute. Because that's how the material shows. Sometimes there's stuff to do, sometimes there's no stuff to do, sometimes there's too much stuff to do. That's the reality. So throwing just picks per minute, these are effective picks. And then we show that here with the client, so this is all the aluminum on the belt, so we can see it all the aluminum on the belt. The red stuff is what the stuff is going to go by. The green stuff is what we're going to capture. Actually, he put a magnet there, so we're going to capture the ferrous here. So we can show him exactly before we build anything that the efficiency of the system, that his stream is going to go from 78% to 85%. Funny enough, right now he's got a guy sitting there like a person, and he's doing exactly that. That person is delivering about 85% purity on the aluminum stream. And he runs this on 2 shifts, so that cost him, that's in the UK, it cost him about 80,000 pounds to pay these 2 people there. Now, next scenario. Oh, so how do we do this? So what could it look like? I hope this is going to start. So the simulator, actually, we simulate, so we take real pics from real life, and we throw it on our simulator, but this is a different one. We calculate the real pics that are going to happen, because if I try to send 1 million pics to the first robot, it's only going to do what it's going to do. Some of them will go back, dispatch to the second robot, some to the third robot. So now we're really calculating, based on your real stream, what this thing is going to do, like how, and yeah, that's it. So then we run into scenario 2. So we take the same stream, we go like, what about we put 2 M10s, that 2 fairly large robots that have toss across capability, and then we run the scenario again. So now again, the same sample, 13 hours, we put 2 robots. Now these 2 robots, as I told you, are supposed to do 30 picks per minute each. But through the simulator, we show that actually they're going to do 42 only. Doesn't matter. And everybody say, hey, your robot is too slow, it's doing this, it's doing that. Now we can calculate value. So now he was at 78% on that simulation. Bringing these 2 robots is going to bring him to 91%. Actually, he was at 85, and now he's looking to up it to 91. That has a lot of value for him selling his product downstream. So now he's starting to see value from aluminum purity increase. It's worth 200 grand for him, plus the labor savings. So actually, and we also say, hey man, we're going to put you more bins there, so that when we actually capture product that we know what we got in our hand, if it's HDPE, we're going to put it in HDPE bin instead of doing this all trash thing. And so actually, you could sell products, additional products out of this. So now we have not determined the value of captured products. But anyway, his payback started look really interesting on 2 robots. Again, this is the aluminum, this is where we're going to capture, this is what it's going to go by, and so on. And finally, the last scenario that we run, and we do this like overnight, this sort of analysis, because we have the simulator, we plug the numbers and the data from the scanner, and that's it. And scenario 3, we said, oh no, this is what we're going to do. We're going to put you a smaller robot, 2 smaller robots, not on the same side, but they're going to work in front of each other. They're smaller, they're faster, but they don't have that toss across reach, because bin allocation, where you're dropping, everything has impact on the effective pick. How many picks you're really going to do? It's not about what Fanuc told you can move, the speed of the robot. This is what you're going to do in real life. You need to know where you're going to drop to figure out that's your real cycle time. So we're here. Again, we run a scenario. Now these 2 guys are doing 47 picks effective, calculated based on all the data, the real data, and now we bring his purity to 92. Boom, now we have a payback. So being able to see, being able to simulate, being able to have gripper AI to say, because in that calculation, not only are we doing this all in theory, we know that grippers are not 100% effective. We have gripper, depending on the type of stuff we're gripping, we're giving a real gripper efficiency on it. So actually, we're going to back these numbers. We're going to guarantee these numbers, and that's where the industry is going with this. So the 3 letter of death, extend their producer responsibility. So not only, so we got all this analytics now. I showed you we can do robotics, we can do this. So this EPR is all about data. So we want to know who to charge, what for, and it's coming. It's in Europe, it's in Canada now, Ontario, Quebec is all switching over. There's few states here that are working on it, and I think there's several. It's kind of really creating a lot of chaos because the regulators are trying to do something that nobody can do. But now, having that sort of data set to be able to calculate things and get ahead of the curve gets really interesting. So you can start doing, well, you've heard all of this before. We put the scanner, we see it all. We have that, we start producing. The interesting thing, we use a 3D scanner, so we have volumetric information that we corroborate in mass, so we can actually do full composition of what's going on the belt in real time. Calculate the number of items, different type of items, volumetrically linked, overflow of belt, raising alarms for clients, what have you. I think there's several of us coming out with this sort of analytics that will allow not only to audit and inform people about EPRs, if they're the designing programs now, you can actually measure things. Not only that, but you can also use it as a benefit for process management in the plant. This, for us, this sort of it's a side product because actually we designed the scanner only to drive the robot, but all that data is there that we're harvesting. Quickly, so as I said, we're kind of a toolbox. So we have different type of robots, different type of grippers, different type of sensors. We use them in real time. So we use suction cups as well, depending on the applications. We do tailored solutions. We don't have like a canned product. Every time we show up at a place, there's already, so we do refuse line, we do bags larger. This thing can lift 50 pounds. We're doing bag sorting in France. That's in Dunkirk in an incinerator. We're capturing the yellow bag, which is full of recyclable. They use that to collect. We do funky stuff like polystyrene spiking. We invented a spiker that spiked polystyrene. So we do food grade versus construction styrofoams, and that helps the client create value. And we do, as well, we do C&D sorting, different type, positive, negative, wood, rocks, bricks, what have you. And so depending on what you want to do, we'll look at it, we'll apply the right sensor, we'll apply the right robot, the right grippers, and we'll come and deliver a solution. We started also getting into, so we have delivered several robots. We're also coming up with meatball picking robot that can actually identify and pick. It's a tough proposition, but it's actually something we started doing. So yeah, hyperspectral robotics sorting. We believe that it's a more expensive robot, but the value proposition is very strong, and the ROI are varying depending on you're running on one shift or two shift. They will vary greatly, but obviously on a two-shift system, most of these payback are under 2 years. Yeah, so that's what I had to say about that. So thank you.
Wow, how impressive. In less than 5 years, we really have a competitive market now for robots. And they're all doing very wonderful things. The brains are getting better, the pickers are getting better, the information's getting better, and it's been done in a very short period of time, getting rid of very dangerous jobs for manual sorting. So anyway, thank you very much. It's time for questions. We have about 8 minutes, I think. So does anybody have questions out there? And if you, right there.
Good morning. Bob, I had a question for you. If I can go back and find it here real quick, I'm sorry. You had shown this slide or your video on the use of the pre-sorting screening for two streams, and you showed where it sat in the plant. For specifically, I'm sorry, for dual stream, I'm sorry, single stream. For what specifically is the application of that unit in single stream? Like, what is it separating from the pre-sort standpoint?
Hello? Can you hear me? Okay. Yeah. Okay. On the single stream side, we've done some separations with fibrous material versus three-dimensional non-fibrous material, and that three-dimensional may then go to something like a ballistic separator afterwards. But with that fibrous material, some of the film plastic would also carry over with some of the on that upper deck, let's say, into the primary line or the oversized line. Along with any bagged waste or any other maybe contaminants that would be in that stream. But I'd say large OCC and some of the contaminants would continue on a primary line. I'm happy to talk to you afterwards too. And actually the gentleman sitting right here from Marpan have one of our screens on the front end of a small single stream operation as well. So if you wanted to chat afterwards, happy to do that.
Hi, this question is about wavelengths. So could you confirm what wavelengths you were looking at for your scanning and your reflectance systems? Yeah, I see. There's a second question there.
I think this is on.
Yeah.
Okay. Yeah, so we generally, I mean, for libs, you can get a good spectrum between 200 and, say, 800. So it really depends on what you're looking at. If we were to be sorting like lithium for some reason, or looking at lithium brines, we would use a higher wavelength. But in general, we're looking between, say, 250 and 450 nanometers. It really depends on what sortation we're looking at. Do you have
So you're doing ultraviolet up through infrared?
Yeah, you can. Yeah,
Okay.
and for most lib systems, the sweet spot is between about 240 and 450 or 500 nanometers.
Why aren't you focusing on the deep UV range?
On the what?
The deep UV range.
TBV.
Deep ultraviolet.
Oh, the deep ultraviolet. Well, so most of the emissions, there are a couple interesting things you can see in the deep ultraviolet, but like in steel, for example, sulfur, a couple other elements, but the emissions usually generally pretty weak. And so given our focus on aluminum magnesium sortation, all the lines that we want, say the aluminum lines, magnesium lines, are all in that sweet spot, 240 to 450. We've done work in the deep ultraviolet, but also below about 180, oxygen kind of eats up all your signal. So
Because when you go into your IR spectrum, you're having a lot more on your range of your percentage of error as well as light interference. So if you're in an open line, that makes it a really like dangerous pick.
Right. So we're doing, yeah, in our situation, since we're doing kind of blowing sort of diversion, you know, it seems to work pretty well. We get over 95%.
Okay. And because you're doing a scan, you have to have a really narrow pick of what you're looking at. Is that correct? You're doing like a spectral scan. So instead of like if you were doing like a reflectance with like, you know, hitting a specific reflectance, you get a snap. You're actually having to do a scan. So it's more, it's not as real time as near real time.
So we're getting the whole spectrum at once.
Yeah.
So looking at the emission, right?
Yeah.
And then we're analyzing that spectrum to look at the elements,
Yeah.
right?
But you
that
don't
are
have any
emitting.
filters that would like, I'll talk to you
Yeah,
later.
let's talk afterward.
But
I'm
there are
happy to go
ways.
through, yeah.
There are ways to increase like the amount of compounds that you could be looking at in a real time situation instead of a near real time.
Sure.
Yeah.
Love to talk afterward.
Any other questions? We have one in the back. And while he's going back there, I'm going to ask one question for each of you, and then we'll take your question. We've got a couple more minutes. So the first question, I'm going to go all the way to the end and ask Eric. In Canada, is your definition or in composition analysis, is it effective for trade? Do you use it for trade? Is that the level that maybe a scale is, where that composition can be used to then pay for the processing fee for, and if not, when is that coming? That's important to everybody here, because waste composition is very expensive. The ROI on your robot, if you can get to that holy grail. So that's the first question.
Well, it depends where. Well, it depends where you place the robot. Like we have a scanner, so composition analysis is as you said, is an expensive proposition. But where do you want to scan? On the front of the MRF, on the back end, before the baler, and trying to grade your bales. So it's up to the people to figure out where it's got the most value. Right now we're in discussion, for example, with an incinerator in Sweden where they pay huge carbon tax if they burn plastic because of carbon emissions. So they would actually scan everything and then use our scanner to back charge the haulers that brought these loads. So every load would be scanned before being put in the incinerator, identify the amount of plastic that goes through, and then go to the hauler and get, hey, here's your tax bill for that, and work with your customer not to bring that much plastic to drive incentives.
So it sounds like it's by contract rather than it's accepted by weights and measures or something like that. Right.
So our scanners on composition analysis, it could be used in several things. So it could be used in contracts with the MRF for measuring the overall efficiency of the MRF. It's given as an operator contract kind of thing. It can be used also on the buyer side, saying, well, it could be used to characterize what they're buying and maybe try to establish a system for back charges for buying products that are substandard. So they break the bale, they put it under the scanner. Most of them will do a resort anyway. So like guys buying HDPE, they want to classify by different type of colors or whatever the type of. So they use the robots for that, but they get the benefit of a scanner having seen all these bales and being able to characterize each of the bale or the loads that are being used. So there are various applications for this. Now we get to, it's kind of a byproduct of the robotic need or the sorting need we have in the first place.
Very good. I'll come back to the other panelists for their question, but let's go to the audience.
Yeah, the question is also about the wavelength. Can you adjust it to use another type, to look for other type of things like lithium, as you said, lithium batteries and that kind of things, and more from the safety point of view for MRFs than for collection or sorting point of view?
Is that for the hyperspectral or for libs? We can probably both answer then. So for libs, certainly. I mean, and we would pick when we design a sorting system, we're looking at, what's the customer trying to sort. So you hone in on different wavelengths, and that allows us to, do a different chemistry with the sorts. And in our system, it's completely designable. So we look at a broad range, and then we analyze specific depending on the sort required. So probably for you too.
Yeah, I heard about battery. I'm not sure if the question was about trying to identify fire issues on MRS or so. Yeah? Yeah. We can train it to see whatever and pick whatever, but the issue often and operationally is that we look at it from the top, so the burden of depth. So if this much thickness on the belt, we don't see through. So we'll see stuff that we can see. So it needs to be liberated. The material needs to be stretched if we want to see it. And one thing I did not mention about robotics, we'd like to bring the conversation from ton per hour to ton per day, because right now there's some MRFs or some guys that are running either CND or whatever, that will run on one shift or two shifts. But the robots, you would never pay somebody to sleep, so why would you have a workforce that is idle at night? So actually, run slower but run longer, kind of. So you see the robots, sometimes we're being tagged like, it's too slow, whatever, but actually it's an infrastructure that can work 24/7. So about stretching, seeing, sorting, ROI. When you move into robotics, you start to need to think differently than what we've been doing for the last 30 years.
Thank you. Thank you. I have a question. It truly is a fact, screens are never going to go away. They're really important to the process, right? Where do you have installed solid waste screens to separate the stream, fractionate them into enriched streams before processing? Solid waste, not C&D, but solid waste.
Yeah, I guess from the solid waste side. Can you turn that one on, please? We have the MSW, if you consider that solid waste, or waste energy is another area where we're separating, doing size separation from larger material to smaller material. Again, it's just like what you said, Michael, about fractionating material streams so you can better handle something that's not 2 foot by 2 foot, on a process. It can only be 6 inches or smaller, going underneath an eddy current or going across a magnet or across a drum magnet, things like that. So a lot of different areas, but the physical size separation is really a critical step to then a secondary process that makes that secondary process that much more effective or much more reliable.
Yeah, but so you have some facilities, reference facilities, Florida or?
Yeah, the MSW operation we had, that was a waste management facility that is no longer in operation anymore, just with some of the changes they've had. But the waste energy operations mentioned, and so those are primarily almost every Covanta facility, Wheelgrader is now WTI, some of those operations, and then obviously the scrap. There's numerous scrap customers, okay. Right, large and small.
Thank you. Any other questions out there before we finish up? One more here.
So you guys talked a lot about the larger material size sort. Has anyone looking into separating out precious metals and things like that from sludge?
Can you turn that mic on, please? Can you turn that microphone on, please, sir? Thank you.
Thank you. Okay. On the screening side, there's fractionating. That's just purely by size, but we do have other technology we implement in the scrap metal side of it. So ASR, auto shred residue material. So there's a high percentage of So that gets for us, that would get more into more I'd say more of like a grinding type operation where we're more on the micron size. That's probably about as small as we get. We do that in some of the mineral-based applications we get involved in. But some of those mineral-based applications are going after gold or other type of precious metal mineral materials, and that could be utilized in one of our machines. It's a grinding mill where we're actually creating a size reduction process that could be done in a solution. That solution can then be run across resin beads. Resin beads could capture, certain different types of precious metal. That's been done. We've got applications where we do that. We do the copper cementation process within some of our grinding mills as well. So it's a totally different application, maybe for a different discussion, but I'm happy to, talk about it.
I'll just add, if anybody, I've been to a lot of different glass facilities in the United States, different vendors, and a lot of them, they'll separate out the metal with a gross eddy current or two, right? And they will get the non-ferrous that isn't aluminum separated from the aluminum, so they get a higher value, maybe an old sheet price on the aluminum. And oftentimes where rings are lost and where precious metals are lost, they end up in the glass stream. And some of those plants were actively collecting the precious metals out of the glass stream, and which I think is great. I mean, I think that was a great exercise, but not all of them do. Not all of them bother to take that step, and there's definitely an ROI there.
Can I just add one more point? Just one other thing I just wanted to mention. This is actually a pretty hot topic in a lot of market spaces right now for recycling, but electric vehicle batteries. That's definitely one of the hot topic buttons that are out there right now. A lot of people that are in the experimentation and building small pilot plant operations and that sort of thing to capture some of that lithium and other mineral-based materials. I mean, everybody knows where the electric vehicle business is going, and the lack of supply of lithium is a major issue. So they're trying to find some really good processes. We're working on several tests right now, trying to figure out some of that technology as well.
Well, I think we're about at the end, unless anybody has a question. And I want to thank everybody. I think this was a great session. There's a bright future for better sorting, better capture, and hopefully making the pie a little bit bigger by capturing more from more difficult streams. So thank you, guys.